In section 4.5, we will discuss how to combine topics from throughout the course to sketch the graph of a function. Let's start with an overview of our graphing strategy. Our first step is to analyze the given function. We need to find the domain of our function. Then we find the intercepts. Recall that the y-intercept occurs when x equals 0, and the x-intercept occurs when y equals 0. Finally, we find the asymptotes of our function. If the given function is a rational function, then the key to finding the horizontal asymptote is to look for the biggest power of x. For example, if the biggest power of x is in the denominator, then the horizontal asymptote is y equals 0. If the biggest power of x appears in both the numerator and the denominator, then the horizontal asymptote is the quotient of the lead coefficients. If the biggest power of x appears in the numerator, then there is no horizontal asymptote. For a vertical asymptote, if the given function is a rational function, then x equals a will be a vertical asymptote if f of a yields a non-zero number in the numerator and a 0 in the denominator. After analyzing the given function, our second step is to analyze the first derivative, f prime. We will use f prime to determine where f is increasing and decreasing and to find all local extrema, that is, all values that are local maximums or local minimums. Step 3 is to analyze the second derivative, f double prime. Here, we will find where f is concave up and down and find all inflection points. Finally, we will be ready to sketch the graph of f. We need to be sure to include in our graph all asymptotes, intercepts, extrema, and inflection points that we found in our first 3 steps. Now, as you can imagine, these are not short problems, so we want to take our time, being sure to complete each step correctly so that our final graph is correct and lines up with all of the information we found. As an example, let's sketch the graph of the function f of x equals 2x plus 1 divided by x plus 1. Our first step, remember, is to analyze the given function. We start by finding the domain. Since f is a rational function, we need to avoid dividing by 0, and so we see that our domain is all values of x except for negative 1. We can write this as the interval negative 1 to negative infinity, union negative 1 to positive infinity. Next, we want to find the x and y intercepts of the function. The y-intercept occurs when x equals 0. We see that f of 0 is 1, and so our y-intercept is the point 0, 1. The x-intercept occurs when y equals 0. If we set our function equal to 0, we have 0 equals 2x plus 1 divided by x plus 1. Multiplying the denominator to the other side, this occurs when 2x plus 1 equals 0, or when x equals negative 1/2. Therefore, our only x-intercept occurs at the point negative 1/2, 0. Now, we want to find the asymptotes of our function. For the horizontal asymptote, we look for the biggest power of x. Note that the biggest power of x, and x to the first power, occurs in both the numerator and the denominator. Therefore, our asymptote will be the quotient of the lead coefficients. Hence, we have y equals 2. For the vertical asymptote, we want to find all values which give us a 0 in the denominator and a non-zero in the numerator. Here, our candidate for the vertical asymptote is x equals negative 1. We can check that f of negative 1 equals negative 1 divided by 0, so we do get a non-zero value in the numerator and a 0 in the denominator as desired. Hence, our only vertical asymptote is x equals negative 1. We are now ready to move on to our second step, which is to analyze the first derivative, f prime. To compute f prime, we need the quotient rule. So we have the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Let's simplify our numerator by distributing the 2 and the minus sign. So we have 2x plus 2 minus 2x minus 1 divided by x plus 1 squared, which simplifies to 1 divided by x plus 1 squared. We need to make a sign chart for f prime. So we need to know when f prime equals 0 or does not exist. F prime equals 0 when the numerator 1 equals 0, which never happens. And so f prime never equals 0. F prime does not exist when the denominator, x plus 1 squared, equals 0. So when x equals negative 1. So on our sign chart for f prime, we only need to plot negative 1. Now this divides our number line into two intervals, all x values less than negative 1 and all numbers greater than negative 1. We need to determine whether our derivative f prime is positive or negative on each of these two intervals, and so we'll use test numbers. First, we need to pick any number less than negative 1. How about x equals negative 2? We evaluate the derivative f prime at negative 2, and we see that we get 1 divided by negative 2 plus 1 squared. The numerator is a positive value, and the denominator is also positive. So altogether, we see that f prime of negative 2 is positive. And so f prime is positive on the interval consisting of all x values less than negative 1. Next, we need to pick a number greater than negative 1. How about x equals 0? We see that f prime of 0 equals 1 divided by 0 plus 1 squared. And so again, we get a positive divided by a positive, hence f prime of 0 is positive. And so f prime is positive on the interval consisting of all x values greater than negative 1. Our third step is to analyze the second derivative, f double prime. Recall that our first derivative equals 1 divided by x plus 1 squared. We can certainly use the quotient rule to differentiate here, but instead, I'm going to rewrite this as x plus 1 to the negative 2 power and use the power rule, which I think is a little bit faster. Our second derivative then is negative 2 times x plus 1 to the negative 3 power, which we can rewrite as negative 2 divided by x plus 1 cubed. We need to make a sign chart for f double prime. So we need to know when f double prime equals 0 and when f double prime does not exist. Note that f double prime equals 0 when the numerator negative 2 equals 0. This obviously is never true, and so our second derivative never equals 0. F double prime does not exist when the denominator x plus 1 cubed equals 0, so when x equals negative 1. So on our sign chart for this second derivative, we only need to plot the value x equals negative 1. Now again, we need to pick a test number from each interval. For the first interval, let's stick with that x equals negative 2. F double prime of negative 2 is negative 2 divided by negative 2 plus 1 cubed. So we have a negative number divided by a negative number. Altogether, this is positive. And so f double prime of negative 2 is positive. And so our second derivative is positive on the interval consisting of all numbers smaller than negative 1. For our second interval, how about a test number x equals 0? Our second derivative at 0 is negative 2 divided by 0 plus 1 cubed. So we have a negative number divided by a positive number. Altogether, this is negative. And so f double prime of 0 is negative. Hence, our second derivative is negative on the interval consisting of all numbers greater than negative 1. Our final step is to sketch the graph of the original function f. Here is a summary of what we found in our first 3 steps. Our domain consists of all x values except for negative 1. We have intercepts at the points 0, 1 and negative 1/2, 0. We have asymptotes of y equals 2 and x equals negative 1. And here are our sign charts for the first and second derivative. From the first derivative, we see that f is increasing from negative infinity to negative 1 and negative 1 to positive infinity. F is never decreasing and has no extrema, so no maximums or minimums. From the second derivative, we see that f is concave up from negative infinity to negative 1 and concave down from negative 1 to infinity. Note that f does change concavity at -1, but this is not an inflection point since it's not in the domain of our function. So f has no inflection points. Before sketching, I like to make one final chart, which I call the big chart. Here, I want to combine all of the information from the sign charts for the first and second derivative. From the first derivative, recall that f is increasing from -infinity to -1, and then again from -1 to +infinity. From the second derivative, we see that f is concave up from -infinity to -1, and concave down from -1 to +infinity. So now when sketching, we'll only look at this one chart, this big chart, instead of having to look at two separate charts. To sketch, let's start by plotting our intercepts, 0, 1, and -1/2, 0, and our asymptotes, y equals 2 and x equals -1. We would also want to plot any extrema and inflection points here if our function had any. Since our example doesn't, then we'll move on. Notice that the vertical asymptote divides the plane into a left and a right half. We'll focus first on what's happening to the left of the vertical asymptote. Since we must respect our vertical and horizontal asymptotes, we have two options for our graph. Either it looks like this or like this. But we know that our function is increasing and concave up for values of x less than -1. And so to be increasing and concave up, we know that we want this. Now, what about to the right of the vertical asymptote? The intercepts make this one a little easier. To respect the asymptotes, our choices are this or this. But we know that f must contain the intercepts that we found, and we know that f is supposed to be increasing and concave up. So our graph must look like this. All right, fantastic. We have now successfully sketched the graph of 2x plus 1 divided by x plus 1. As promised, these are long problems. You want to take your time so that all of your information lines up and leads to the correct graph. We will have plenty more examples in class, and I look forward to seeing you there.